Welcome to the deep dive. Today, we're really getting into something pretty high stakes. An IT project involving replacing core network software across hundreds, literally hundreds of active bank branches.
Yeah, we're talking about upgrading Cisco IOS. That's basically the brain, the operating system for their main network routers. And this was across about 850 bank branches in Germany, the stakes. Immense, really.
Immense how, like, what happens if it goes wrong?
Well, if an upgrade fails, that branch just stops
Hmm.
completely.
Hmm.
No ATMs, point of sale doesn't work, internal systems are down, all connectivity is just gone.
Hmm.
So, yeah, the potential for catastrophic downtime. That was the number one thing hanging over this whole project.
Okay, so this isn't just, a tech challenge. It sounds more like a masterclass in, well, risk management. Because they knew something was already wrong, didn't they? There was a known issue.
That's right. They weren't going in totally blind. They knew their standard method using Cisco Prime, which, is the normal tool for managing lots of Cisco devices. It actually had this dangerous little flaw.
A flaw? What kind of flaw?
Sometimes, when Prime copied that big iOS software file over to the router, the download would get corrupted. Just slightly, maybe. But enough that the MD5 checksum, the file's fingerprint, was wrong.
And a bad checksum means?
It means the router just wouldn't boot up with the new software. It sees the file's damaged and, well, refuses to start. So you've got a dead router and a dead branch.
Right. So the whole mission shifted then. It wasn't just update 850 routers. It became, how do you possibly scale this super risky update, do it overnight, automatically, and guarantee you sidestep that corruption problem every single time?
Exactly. And the answer was this custom-built Python script.
Yeah.
It wasn't really designed for speed, although it's efficient. Its main job was risk management, checking integrity, and basically protecting itself and the engineer from failure.
A defensive process, not just an upgrade tool.
Precisely. The engineer realized, look, I'm not trying to save 5 minutes copying a file here. I need a bulletproof process.
Yeah.
The goal wasn't just speed. It was absolute, verifiable operational continuity, nothing less.
Okay, so let's dig into how that defense worked. They still use Cisco Prime for part of it, right? Why use the tool if you knew it sometimes messed up the files? Seems a bit risky.
Well, it's about using the right tool for the right job, where it makes sense. Prime is still genuinely the fastest way to just get that big software file onto all 850 devices. Think of it like bulk delivery.
Okay, so Prime did the initial brute force copy.
Exactly. It got the file onto the router's flash memory. Quick and dirty, you could say. But that's where Prime's job ended. Then the Python script woke up and took over as the quality control inspector.
And this Python script, where was it actually running from?
It was running on a standard Linux server, Ubuntu probably. You'd often call it a jump server or management station. It had secure network access, SSH access, to all 850 routers using the engineer's own credentials.
So first job for the script, tackle that corruption risk head on.
Absolutely. Job number one, the script logs into the router, and the very first thing it does is run the command to calculate the MD5 hash of that iOS file Prime just copied.
That digital fingerprint we talked about.
Precisely. It's a unique signature for that specific file. If even one single bit is wrong, that hash value changes completely. There's no ambiguity.
And checking the hash on a big OS file, that's not instant, is it? Takes a bit of processing power.
No, it takes the router CPU maybe 1 or 2 minutes usually. It has to read the entire file. Then it spits out this long string of hexadecimal characters.
Okay, so the script gets this hash. Then what?
Then it compares that calculated hash against the original official MD5 hash that Cisco publishes right there on their software download page. The known good value.
Ah, I see. So it's not guessing. It's actually proving the file is perfect before it even thinks about doing anything risky like rebooting.
Exactly right. It completely takes that known Prime bug off the table if the hashes don't match. The script immediately flags it as a failure for that router, logs it, and just stops. It won't attempt the reboot. It moves on to the next device on the list.
So you go from maybe trusting a slightly dodgy copy process to, well, mathematical certainty about the file integrity?
That's it. Trust, but verify, automated.
Okay, that handles the big technical risk, the corrupted file. But, even if the file's perfect, things can still go wrong or seem to go wrong. What was the next big fear? It sounds like it was less about the tech and more about managing blame.
You've hit it exactly. This is where the process gets really smart, I think. It moves beyond just engineering into, well, liability management. Or maybe just call it CYA, covering your asset.
Defensive documentation, as I was thinking of it. Protecting yourself.
Absolutely. So before the script even considers sending that reboot command, it runs a whole battery of commands to capture a snapshot, a really detailed, time-stamped picture of exactly how that router and its network look right now.
Like an alibi, almost. What kind of information does it grab?
Oh, quite a bit. Standard stuff, but crucial. It
Yeah.
runs show version to document, exactly what software is running now. It runs show up interfaces brief to see which connections are up, which are down.
Standard network engineer checks.
Right. And also things like show CDP neighbors to see what other Cisco devices it's directly connected to, and show ARP to see what IP addresses it knows about on the local network. It builds a map, essentially.
Okay, that makes sense. But you mentioned one test was even more critical for this defensive part. The reachability test. Pinging everything. Why go that far?
Ah, yeah, that was the, let's call it the silver bullet for self-protection. Think about a bank branch. It's not just the router. You've got maybe customer kiosks, special teller terminals, maybe VoIP phones, printers, security cameras, backup systems, tons of devices.
All relying on that router being up and working correctly.
Exactly. And if one of those things, say specific printer, isn't working the next morning after the upgrade, what's the first thing the branch manager is going to think?
The upgrade broke my printer.
Precisely. So the script, before rebooting, pings every single IP address it can find listed in the router's configuration for that branch. Every single one. And it carefully logs which ones respond, and crucially, which ones don't respond.
Ah, so it creates this baseline. Hard evidence of what was working and what wasn't before the upgrade touched anything.
Undeniable proof.
Hmm.
It draws a very clear line in the sand. Look, Mr. Branch Manager, we can see that printer at IP address 10.1.150 wasn't responding to pings at 1:59 a.m. before we rebooted the router. So while we sympathize, its problem isn't related to our upgrade activity.
That's clever. It defines the scope of responsibility very, very clearly. Okay, so integrity checked, defensive documents collected. Now it's time for the actual upgrade. Section 3, execution. This had to happen late at night, right?
Oh, yeah, absolutely.
That's
Banks, this had to be completely invisible to staff and customers. So typically scheduled for maybe 2:00 a.m. when the branch is definitely closed, network traffic is minimal.
And the engineer doesn't stay up all night watching it.
No, that's the beauty of the automation. The engineer would maybe set it up around 5:00 or 6:00 p.m., feed the script, the list of IP addresses for that night's batch, say 20 or 25 routers, set the start time for 2:00 a.m., and then go home.
Trusting the script, how did it handle that batch? Did it blast them all at once?
No, absolutely not. That'd be far too risky.
Hmm.
The discipline here was key. It processed the list strictly one router at a time, sequentially.
Why sequential? Seems slower.
Damage limitation.
Yeah.
If there was some unexpected problem, maybe a weird interaction with that specific router model, or a subtle bug in the new iOS version that only showed up on certain hardware, doing it one by one means you only affect one branch, not 20.
Okay, makes sense. So for each router, it gets the all clear after documentation. Then what? How does it reboot?
It uses an SNMP command. That's a common network management protocol. It sends a specific instruction telling the router, okay, reboot now using this new iOS file we already verified.
And then the script just waits?
It waits, but it's actively monitoring. As soon as it sends the reboot command, it starts pinging the router's management IP address continuously. Just ping, 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 waiting for it to come back online.
How long does that usually take?
Typically, maybe 2 to 5 minutes for a router like that to fully boot up, load the new OS, and get its network interfaces working again. Once the pings start succeeding consistently, the script knows the router is, well, alive.
Okay, router's back online. But now comes maybe the most critical part of the risk management, the feature that really made this whole thing viable at scale, the stop on failure feature.
Yes, this is the absolute core of why this worked so well and why the engineer felt confident scaling it. If for any reason that router doesn't come back up within a reasonable timeout period, let's say 10 minutes.
Or if it comes up, but maybe fails some later checks we'll talk about.
Right. Or if any verification step after the reboot fails, the script immediately stops processing the entire list for that night. It just halts. It cancels the remaining, say, 19 or 24 routers that were scheduled after this one.
So one failure doesn't cascade into 20 failures?
Exactly. It contains the problem. The engineer might wake up to an alert about one failed branch, but not 20. It acts like an emergency brake for the whole batch process.
That must provide incredible peace of mind. Knowing that a single unforeseen issue, maybe some rare hardware fault on router number 1, won't take down the whole night's work while you're asleep.
It's fundamental. That confidence, that containment system is what allows you to even consider scaling something like this to hundreds or even thousands of devices. Without that safety net, you wouldn't dare automate it like this.
Okay, so assuming the router does come back up, responds to pings, or we're not done yet, right? We need to make sure it actually worked. Section 4, post-upgrade verification.
Right. The audit trail continues. As soon as that router is confirmed up via ping, the script logs back in and runs the exact same set of documentation commands it ran before the reboot.
Mirroring the before snapshot.
Precisely. Show version, show EPIP interfaces brief, show CDP neighbors, show ARP, and crucially, that full reachability ping test against all the IP addresses in the branch.
And what defines success at this stage? What does the script check for?
Two main things. First, the obvious one. Does the output of show version now clearly show the new Cisco iOS version running? That confirms the upgrade itself technically happened.
Makes sense. What's the second check?
This is the liability check again. It compares the results of the after reachability test, which IPs responded, which didn't, against the results of the before reachability test.
And they have to be identical.
They have to be absolutely identical. If a printer was reachable before the reboot, it must be reachable after. If a phone was unreachable before, it must still be unreachable after. Any difference implies the upgrade process itself changed the operational state of something on the network, beyond just the router's OS.
Which is exactly what you want to avoid, or at least document clearly if it happens, though ideally it shouldn't.
Right. The goal is to prove the upgrade only changed the iOS version and didn't break anything else that was previously working.
And all this data, the before commands, the after commands, the comparison results, where does it go?
It's all saved automatically by the script into text files on that Linux jump server. The file names are really clear, usually including the router's IP address, the date and the time, maybe labeled before boot and after reboot, makes it super easy to find and compare later if needed.
Which circles right back to that payoff, that ultimate defensive shield. The next afternoon, the phone rings. Branch manager says, hey, our special secure terminal in the back office is down since your upgrade last night.
Yep. And the engineer's first move isn't panic. It's, okay, let me check the logs. They pull up the before file for that branch's router, find the IP of that terminal, and check its status from 1:59 a.m.
And if the log shows it was already unreachable then?
Then the engineer can calmly and with proof say, actually, I see here that terminal wasn't responding even before our maintenance window started. The issue seems unrelated to the iOS upgrade itself. Conversation changes completely.
That detailed automated audit trail turns a potentially messy he said, she said situation into something objective and verifiable. It defines responsibility.
Absolutely. And the outcome. Well, the project was a huge success. They upgraded roughly 850 Cisco routers across Germany. Zero reported downtime attributed to the upgrade process itself. Customer satisfaction was, as you can imagine, very high.
And the engineer's confidence in the process itself.
Massively boosted. The feeling wasn't just, phew, we finished. It was more like, okay, we've cracked it. We have a system here that's so safe, so documented, so self-protecting. We could do 1,000 routers next week, or 2,000, or 10,000. The fear of scaling just evaporated because the process itself was so robust.
So wrapping this up, what's the big takeaway for us, for the listeners? It seems the core lesson isn't purely technical.
No, I don't think it is. It's that in these really complex, high-stakes rollouts, sometimes the biggest risks aren't the obvious technical bugs. They're often process risks. Things like accidental data corruption during a standard step, or managing customer perceptions and blame after the fact, or just the sheer anxiety of trying to do something risky hundreds of times over.
And automation, when it's done right, isn't just about speed.
Exactly. Yeah. Here, automation, specifically combined with that obsessive level of pre- and post-documentation, turned what could have been a nerve-wracking manual slog into something repeatable, auditable, and frankly safe. It was the rigorous documentation that really gave them the license to automate and scale confidently.
It's fascinating. The engineer effectively built a defensive weapon, a liability shield, disguised as a simple upgrade script. Its job was twofold. Install the software, yes, but also produce irrefutable proof of exactly what did and didn't happen.
Which really leaves you with a final thought, doesn't it?
Yeah.
If the real genius here was creating that automated before and after picture, what other process do you have, maybe in your work or your projects, that are high stakes or often lead to disagreements or finger pointing?
Where could applying this kind of automated, comprehensive before and after documentation turn potential arguments and liability into just clear, objective, verifiable proof?
That might be the next really valuable automation project, just waiting for someone to build it.